would like to welcome Monsieur Vincent Drevelle, who's going to present his work on improving guaranteed coverage assessment of the robotic survey in a translation invariant case.
Thank you. So I'm talking about basically assessing the coverage mission by a robot and using the table analysis method. So what are we talking about? Basically, we have a robot just to move in a given area, and is equipped with a sensor or a tool. And what we want to do is to ensure that the given area has been totally covered by the tool or the sensor. So the applications are basically mapping, mind hunting, search for the sensor, like sonar. But if you have a tool like the blade, it could be a lawn mowing. You want to ensure that the whole grass has been cut. And basically, in the sensing problem, the idea is to be able to ensure before retrieving the sensor data that the zone has been covered, because, for example, in submarine underwater robotics, communication is a difficult thing. We have low bandwidth, so we want to get less data as possible, especially just navigation data. Compute the zone that has been explored, and then if we are sure everything is okay, we can get the submarine back on the boat. If we're not sure, we can plan another mission or check the data, but only a part of the data that corresponds to the uncertain area. But in practice, the robot positioning is uncertain, so we want to characterize the explored area with respect to the submarine, the robot, local dimension uncertainty. And we want to do this in a guaranteed way, using interval analysis to compute basically a lower and upper bound of the zone that has been covered by the robot. So basically, I'll just present you first the problem with drawings, and then we will further explaining you how to compute the zone that has been covered, a lower bound and an upper bound. And I'll show you a toy example at the end. So let's explain this with basically drawings. So we have an exploration robot, which is here a submarine. So we can describe it with basically a solution with differential equation, and if it has observation to basically GPS measurements or what kind of ranging sensors, you can correct this position. And so we have this observation equation that links the robot state X with the measurements that are used for position. So just now, if we add to the robot a sensor to mapping, for example, like a sonar or camera, at a given time t, the sensor is seeing a given zone of the sensitive space, which is basically the space we want to map or to cover. And basically, we can also define a set value function, v, which is the set of all the points in the sensitive space that are visible by the robot sensor at time t. So here it's made it's v of t, but as you can see, basically it's v of x of t. It's a function also of the state of the robot. And how to define if a point is visible or not? We use just the visibility predicates, which is true if the point z is visible from state x of t. The way to define it basically is often to use an inequality constraint. You have a function which is negative when the point is. So it's for the visible. And basically we do a mission. So what we want to know is what has been covered during the mission. So it's the covered zone, which is basically only the union of all the visible zones during the whole mission. So that's the problem, but here there was no uncertainty at all, so it's simple. We'll not talk about the uncertain covered zone. And we'll do all the things. So first the trajectory, then the visible zone, then the covered zone. So first, the trajectory is uncertain in practice because we don't have exact knowledge of the intuitive of the evolution model, and we don't also have exact measurements. So if we had bounded errors on U and Y, we can define the set of admissible trajectories of the robot. We call it T, which is basically the solution of this differential inclusion, and we have also this constraint, which is related to the measurement that the robot makes that can correct the position at some times. So it is general. Sometimes the robot does not have any sensor to relocalize, so we will have an initial condition and this differential inclusion, but no. So this is a set of all the trajectories that are admissible, and basically this set also defines the tube of all the visible states at given times. So system X for each time t corresponds to the set of all the states, possible states for the robot. So here, the problem with the uncertainty, so everything becomes no blur, because we don't know exactly where the robot is, so we don't know exactly what is in the scene, and we don't know exactly what is the covered area. What we know is just that we have these admissible trajectories that are defined by the previous equations. So when I talk about defining a tube, here, if we only consider the tube and not the set of feasible trajectories, we see that the tube only represents what are the feasible states at each time. So only having the tube, in the tube you also have unfeasible trajectories, including the set of feasible trajectories. But if you consider the tube, which is basically sizes of this, we also have all these trajectories that are not feasible. But since we consider a tube, the softness information is lost. And so there's more trajectories in the tube than in the set of feasible trajectories. And moreover, if we approximate this feasible state not by an exact set, but by an interval, for example, so we use an interval tube, basically, then we have the warping effect that applies to, and for example, if there is a branch, it's not an interval anymore, it's a union interval. If there is basically we have the warping effect. So you also have pessimism due to if we approximate the feasible state at given time by an interval. So that's what we have at a given time. We have a set of feasible states. So to this set of feasible states corresponds now an uncertain visible zone. And basically I will explain it later, but we can probably find some points that we are sure that are seen, find some points that maybe been seen, maybe not, and find some points that are not seen for sure. So basically it's a set interval that contains the visible zone at a given time. And for the covered zone, it's the same, it's uncertain, so it's not set, an uncertain set in this case. So we have a set intervals that bounds the actual zone that has been covered during the mission. So let's start with the uncertain visible zone. So basically, we can bound the visible zone at a given time between the guaranteed visible zone, which is a set of points that are visible for every state in the possible states at a given time, and the possible visible zone that are seen at least one state of the visible state. And therefore, the bracketing of the actual visible zone at that time. So just an example. So here it's a possible example. The position of the robot is represented by the boxes. And the visibility predicate corresponds to a disk around the robot. So if we know perfectly where the robot is, we have this guaranteed visible zone here, which is a disk. If we don't know where it is, the visible zone becomes empty. If we, as the uncertainty of the position grows, and also as the position uncertainty grows, the possible visible zone also grows. And in blue here are points that we are sure that have not been seen by the robot. So if we go to the next level, which is what has been seen during the mission, not at a given time, we will not talk about the guaranteed and the possibly covered zone. Even more clever names because it's a bit long. So we can bracket the covered zone between two sets. The guaranteed covered zone, which we call the clear zone, which is basically the set of points that for every feasible trajectories have been, at least at one time, be seen by the robot. So basically, it's the union for the intersection, sorry, for all the feasible trajectories of their corresponding covered zone. So it's the union of the covered zone by all the feasible trajectories. And we have the possibly covered zone, which is the non-dark zone. Classic, which is basically the union of the covered zones for every admissible trajectory. And the difference, so the boundary zone here is in red, the clear zone. The dark zone is here, the non-dark zone is this. And we call the penumbra the difference between the non-dark zone and the covered, which is the zone from which we cannot decide if it has been seen or not. So to compute the non-dark zone first, basically, so we know it's the union of all the feasible trajectories of the covered zones. So we can express it also in terms of the covered area at each time. It's union of the union. And if we switch, basically we can express it as the union of the possibly visible zones of the feasible states at each time. So it can be expressed indeed as a function of the tube. And if we have the tightest tube corresponding to the feasible trajectories, we have the equality, we compute this zone from the tube. In practice, we don't have the tightest tube because we wrap it into a box, for example. So we will have an upper bound of the non-dark zone. For the clear zone, it's not the same because it's an intersection of the covered zones for every feasible trajectory. And if we put it in terms of the visible zones, we have this intersection of union field, and if we cannot invert both while keeping the equality, so we only have an inclusion here if we switch. The idea of switching is to, instead of working with a set of feasible trajectory, which is not really representable, we want to work with a tube, which we can work with. So we switch so that we can work with the tube, but then we only have an inclusion. We don't have the equality. So we have a lower bound of the clear zone. We compute with even with the tightest possible tube. And of course, it generalizes if we don't even have the tightest tube. If we have another approximating tube, we also have a lower bound of the clear zone. So we have pessimism when computing this zone with tubes. So how to do it? First, we compute the trajectory tube. If we want to have, we can compute the upper bound of the non-dark zone basically by computing this union. And we compute the lower bound of the clear zone using also the union, as shown in the previous slides. And in implementation, to get faster, we can do quantifier elimination in the expressions of the visible, guaranteed and possible visible zones. Also, we don't compute explicitly each visible zone and then do the union because it's too costly, so we defer the computation, the evaluation just at last time. And I also have in the implementation multi-way resolution tubes in time to also increase the speed, basically by pruning parts of the tube that are not needed. So it leads to very fast results, but basically the most problem is with the clear zone, which is a lot under approximated, and it may sometimes be just empty if we have great position uncertainty. So to improve the cover zone bounds, what we can do is to split the trajectory, the feasible trajectories. And to do this, we can decide to split the tube at a given time. So we choose a time, TS, and basically we split the tube into 2, 3, 4, any number of parts. I show it only with 2 parts. And in the initial tube, we have here all these unfeasible trajectories. We split. Then we can apply, we can do constant propagation with the evolution equation to refine the tubes, and it will eliminate some of the infeasible trajectories that were present. So it will reduce basically the pessimisms that we have. And indeed, we have several tubes instead of one to represent our trajectories. So basically, to do this, we choose a given time, we split the tubes, we compute the clear and non-dark zone for all these subtubes, and then to merge them, to compute the clear zone, we have to do the intersection of the clear zone of the subtubes, and to compute the non-dark zone, we have to do the union. So we split at one time, so if we do this, basically the results will be locally improved around this time of the trajectory, so we can split at different times of the trajectory to improve globally the results. So it leads to very great improvements, but it increases computation time a lot, especially if you have a lot of uncertainty, because we have to divide in very small subtubes in complexity than is needed. So I try to do this very fast because it's really late. So in practice, in robotics, most real case scenarios, the space we want to cover, basically, corresponds to a subspace of several components of the robot. Basically, we want to map something by latitude and longitude, and in the robot state, we will have this corresponding latitude and longitude. So the robot sees the same latitude and longitude. So we have this correspondence. And since the sensor is attached to the robot, both moves the same. So we can decide to split the state vector of the robot in two parts. One part, XA, that basically corresponds to the sense space, and XB, which corresponds to other parts of the states that are independent of the sense space. And we will say that the visibility predicate is a translation invariant, so it's not both are not in Rn. This part is in R cube, and this part is in Rn. If basically, when we have a translation of vector A in the first component of the state space of the robot, we have the same translation in the sensing space. So that's here. So if the robot has moved 1 kilometer to the north, the state is 1 kilometer to the north, the same space, the visible zone is the same, but 1 kilometer to the north. So it's basically transition in that. And it is very common in our applications. And to represent the emissive trajectory, what we use is basically, instead of having a tube or dividing the tubes, we will use what I call the parallel tube bundle, which is basically a tube, small, and a translation domain. And this parallel tube bundle is basically the set of all these tubes translated by this translation domain. So we represent this way the possible trajectories, and we see that if we start from here, we cannot go there because we have to follow one of these tubes. So we keep more of the information of the flow. And basically, when we do this, it's locally at some time of the trajectory. And in this case, basically, so we can find a tube and a domain such that the parallel tube bundle that corresponds basically contains all the physical trajectory. We want to do this in a tight manner. And in this case, if the visibility predicate is translation invariant, then the guaranteed covered zone is given by the microscopic difference of the guaranteed covered zone compute with only the small tube. And then we do the difference with minus A, where A is the translation domain. So the proof is the file. And basically, this can give a lower bound of the clear. So what we do is basically we compute tubes like before, and we do this approximation locally at different times to improve the result. So basically, just an example. So a robot, its trajectory, its uncertainty in blue. So here it's well localized, here is not well localized. And if we use the first method, which is very fast, which is just the union of visible zone, in the first case we can compute a great clear zone, but here the clear zone is very reduced because of position uncertainty. And if you use the parallel tube bundles, then erosion method, in the well localized case, doesn't change a lot because there was no uncertainty at all, but we can prove a larger clear zone in this case with very rather low computational cost. Okay, so basically that's already late. I'm already late, but the idea is that using Drevelle analysis, we are able to compute and to guarantee that some points in space have been seen by a robot, some points have not. It's sometimes very complicated, but when we have this tight relation between robot position and visible area, we can do it in a very fast way using simply erosion of another computing zone. So thank you.
Okay, thank you, Vincent. Are there any questions on this presentation?
Yes, one question. On the previous slide, where is the beginning of the trajectory?
At the center. Yeah, so the robot basically looks like this.
Okay.
And here too, but here at the start, basically, we know just that it is inside this big box.
Yes. So why after? So the next slide, I don't understand why you okay. So the white part. Okay. So at the beginning, the white part is.
So here, if we only use the union of the visible zone at each time, since here the uncertainty is already large, we can just prove that we see this, and then uncertainty grows, and here we cannot prove anything.
Okay. So you take different times, and then you apply the first algorithm.
So basically, I take different times, but in this case, just using the start time is okay. And then we locally approximate the trajectory tube by a small tube and a translation, and we compute with this, and then we can.
Okay. So the gray is a penumbra.
And the gray is the penumbra, but it doesn't improve the penumbra using this.
Any other question? Okay. I'd like to thank Vincent Verdier